Right. I think I found the issue finally. Uh, the audio should be working now. Just let me check. Yes. All right. Sorry about that slight delay. Uh, okay. Right. So sorry about that. I started the workshop not knowing that you couldn't hear me. Anyway. So yeah, Grasshopper is, as you all probably know, a plugin for Rhinoceros, which we are going to talk about today mainly. I am going to assume that most of you are designers or architects or engineers who have some basic idea of how 3D works, and I hope you all have Grasshopper, Rhino and Grasshopper installed. If not, I've mentioned a link to Rhino in the chat and the description as well. You can download the 90-day trial for free from their official website. And Grasshopper is pre-installed in Rhino 6, so you don't have to worry about installing anything after that. Uh, right, so I'll just get started. I'm Praneet Mathur. I am a trained architect, but I have sort of uh, a keen interest in technology and everything that is in the intersection of technology and design. So I have quite a lot of experience with Grasshopper, and I even develop plugins and scripts for Grasshopper to aid design. Right. So uh, Grasshopper is, I know a lot of people have this sort of, they're kind of scared when they see Grasshopper scripts for the first time for the reason that they see that it's all these wires and nodes and extremely complicated stuff, and they assume that you'd have to be some sort of uh, computer engineer or something to be able to actually work with all this, but that's not at all true. And hopefully by the end of this, you will be much more confident in picking up Grasshopper and using it as a tool daily in your design and in various other ways. Uh, so if you have just installed Grasshopper, just installed Rhino and Grasshopper, then it will probably not look exactly like it looks in on my screen, because I have installed quite a lot of plugins, and my Rhino is also sort of dark themed, and so don't get don't be confused by that. You should be able to see these, at least the first few tabs in Grasshopper. These are the default tabs. The rest of these are all plugins, so you don't have to worry about those. We will start off with these first, and I will explain eventually how plugins work, how to install plugins, and what all plugins do what. So which ones you should install depending on what you want to do. So first of all, I want to explain why Grasshopper is an important tool, uh, and why designers today have started using it so much. Uh, it all starts. I mean, so think of it this way: the pen, pencil, paper, those are also basically what we call tools for designers, right? They uh, enable us to communicate our thoughts and our ideas in a way that others are able to understand. Similarly, SketchUp, AutoCAD, all these other software also do the same thing. Here, Grasshopper does that exactly, but the only difference, what sets Grasshopper apart is that it's parametric, which means that you can go and sort of tell the computer how you're thinking and how you want your design to be developed. And so you can always go back and change a parameter, change some, set some values differently, and the computer, already understanding how your design is developed, will sort of run that same script that you've created and give you another iteration of that same design based on the change in your parameter. Now, that might have sounded a bit confusing to some of you, but you'll understand as we go forward. Right. Now, I'll just start off by explaining what you see on the screen. So, this top part here is called the ribbon, where we have tabs, and each of those tabs have these categories with all these icons. Right. So these are all basically components. And what components are is those nodes that you see. So I'll just create one of these here. Right. So this is a center box component. Now, if it doesn't appear exactly this way, it might say, B, X, Y, Z, and B here, and this might be shorter for some reason. You can change that by going to display and selecting draw full names. That will make sure that the entire name of each of these is visible. Right. So this is a very basic component. The I would say a normal component is this is an example of a normal component. Right. So you have your inputs at your left, the name of the component in the middle, and the outputs on the right. And these are basically the nodes, right? Now, this is not the only type of component that is out there. There are components which only have outputs, like our number slider. There are components which have only inputs, like the custom preview component. And there are components which don't really have any function but to store data, right? So there are essentially four types of components, right? These are called input components. You can see all of them here, and there are some featured in a couple of plugins as well. So these components take input in various forms and give only output, which can be used, uh, you know, to that data then can be used in other components, right? Then we have components which are parameters. These don't actually do anything other than just storing data, right? Uh, and we'll come to what data implies. Like this particular parameter will store points, right? And we'll come to storing data and how data works later on, right? This component, of course, is a normal component which has one function. It will take inputs, perform that function on that input, and give you an output, right? And then we have components which take only input and do something using that input, but don't necessarily give an output, right? Now, all of this input, output, and data jargon might be a little confusing to you, so I'll switch to the Rhino viewport. And here you'll see that if you've never used Rhino before, but if you're used to maybe AutoCAD or SketchUp, you will know that you'll understand the concept of commands, right? So if in SketchUp you want to draw a line, you'll select the line tool, and you'll select 2 points, and you're done. You have a line, right? And similarly in AutoCAD, you can do the same. Now, what happens in the background, AutoCAD users will understand this, is that actually you are entering a command called line, and then you're entering parameters, right? The start of the line and the end of the line. So I can enter, say, 000 as the start, and my end could be, say, 0050, right? So I have a vertical line which is 50 units long in the z direction, right? Now, 000 and 0050 were the parameters that I gave this command to create this line, right? Similarly, if I take a look at the line component in Grasshopper, here you'll see that this also takes just two inputs, the start point and the end point, just like we did in Rhino just now, right? So I can simply right click on this, say set 1 point, and then I can go to my Rhino viewport and set 1 point, right? And come back to this and set another point. And there we go. We have a line between the 2 points, just like that. Right now, the reason why this line appears slightly different from the one that we made in Rhino is because you can think of this line as imaginary. Whatever geometry Grasshopper deals with is represented in the Rhino viewport in this sort of translucent red color, and only when the component that actually is giving that geometry as an output is selected. So when I select this component, that red geometry will become green because the component that's producing that geometry is selected. So that's a really easy way of understanding how geometry behaves within Grasshopper. So you can think of it as instructions in your head. So when you think of your line, even in your head, you're imagining this line that goes from 0 to 50 in the z direction. So think of Grasshopper's geometry as that geometry that is in your imagination, right? And then if you in your imagination change a parameter, so for example, I change my start point, the same will actually change in Grasshopper. That line will also change. The output of that component will change as well if the input changes. Now, this was a very, of course, crude example. So what I'll do now is I'll explain it in I'll draw a parallel to, say, baking a cake, right? So when you bake a cake or you cook anything, you have a recipe and a set of instructions. So uh, when you say, bake a cake, which has to be, chocolate flavored with some icing and a cherry on top, right? That is the instruction for baking the cake. If you just say bake a cake, you know, a dumb machine like a computer would not know what to do because you have given it no details, no parameters, nothing to bake the cake with. Similarly, if you just tell a computer to draw a line, it won't be able to, right? That is why these components will have an input and an output. Now, these are called functions, right? In programming language, uh, I mean, in programming lingo, these are called functions, right? Which take an input and give you an output. Now, the last place where you might have heard these functions, if you don't know programming at all, would be Excel, right? In Excel, you will have these f of x sort of, you can actually enter a function into a cell and say something like this cell should be equal to that cell plus this cell, and then the value of that cell will change to the sum of those two cells. So that is a function that actually defines the value of that particular cell. So these are essentially functions, and Grasshopper is in its by nature is a function based visual scripting tool. So that means that you are actually programming, you're giving instructions to the computer, just that you're not having to write any code by actually typing words, and you're just doing it visually. So it's a visual scripting tool which is function based. Now, the other kind of programming is event based, which means that when you click on something or when you drag something, those kind of events are captured. So we will not get into that because Grasshopper doesn't really deal with that directly. So right. So now that that is aside, I'll continue with a simple example. Right. So let's actually make a short script. Let's say I want to make a very simple box, right? So I'll say box. So what I did here is I double clicked on the canvas. This is my canvas, this area, and I can either sort of search for the component that I want to use here, or I can simply double click and start typing. So it'll automatically search for uh, you know components based on what I'm typing. So I've double clicked and I'm going to type box. So it gives me all of these various components that have something or the other to do with boxes. So I'm going to select a center box, and you'll see here in my Rhino viewport that it creates this red imaginary box, which is 1 by 1 by 1 in dimension, right? And its base is world XY, which means it's on the XY plane of the world, which is at 0, 0, 0. So I don't want the box to be 1 by 1 by 1. I want it to be, say, 10 by 15 by 30. Right. So what I did here is I double clicked and I just entered a number, and as soon as you click on number slider, it will simply create one of these number slider input components, which basically holds a value and lets you change that value within a range. Right? It's like those sliders you see on DJ turntables. They sort of you can change the value by just sliding this diamond around, right? So I'm going to plug these nodes in as my X, Y, and Z, and you'll see that as I was plugging them in, the values changed in my model as well, and my box looks the way I expected it to, right? And if I go ahead and change these values, the size of my box changes as well. Now, a question you might have is, what if you want, say, in this particular number slider, what if you want the value to go beyond 10? Well, there are multiple ways of creating a number slider. One, of course, is by dragging this in. The other is to simply type the number in. Another really quick way that I use a lot is to simply enter the lower limit of your slider that you want. So I want the minimum value to be not 0, actually 1. And I want the default value to be 10. And I want the maximum value to be, say, 40, right? And so I've entered 1, less than 10, less than 40. And the moment I hit enter, it'll create a slider whose values can range from 1 to 40, and the default value is 10, right? And if for example you've already created this and you've plugged this in, and you don't want to go ahead and create another number slider to replace it, you can simply double click on the text where it says number slider, and it'll open this neat dialog box for you where you can change the properties of the number slider. So you can even change it to actually contain to actually give you use rational numbers instead of integer numbers, and so you can define the maximum number of decimal points that basically it's accuracy. So I'll set this to 3, so I can actually enter a value of 11.564, something like that, right? Now, this is really useful because Rhino is an extremely accurate modeling tool. I mean, it's so accurate that its primary use initially was for jewelry designs. So it's extremely accurate to the extent that you can work in nanometers and even at astronomical units. So especially for architects and product designers, this is really useful. Uh, this is a really useful feature because you can enter like to the last millimeter, you can have really accurate values. And if you wanted to create, say, a slider like I have here, without having to change its properties and actually have decimal points, you can simply enter that number of decimal points. So I'll enter 1 less than 10.000 less than 40, and it will create a number slider with 3 decimal points. Right. And so this is a very basic script which lets me create a box with any x, y, and z dimensions, and just copy this same number slider. Of course, Control C, Control V works here as well. So you can copy and paste any of these components as you wish. Right. So now that I have this, say now I want to do something with this box. Right. I want to for example, I want to get the center or the volume of this box, right? So if I just double click and enter volume, I'll get this component which takes any kind of geometry, a closed prep actually. Okay. Another thing is if you leave your cursor hovering on any of these parameters, the input parameters, output parameters, uh, these components usually give you a description of what kind of input it's expecting or what kind of output it will give. So for this component, like if I have never seen this component before, I can simply leave my cursor on the parameters and I can understand what this component does and what kind of inputs it needs and what kind of outputs it will give. So here it says it requires a closed brep or mesh for volume computation. We'll come to what breps and meshes are, but for now just understand that it takes geometry in and it gives me the volume of the geometry and the volume centroid of the geometry, right? And if you leave your cursor on the name of the component, it'll even tell you like a brief description of that component itself. So I'll plug this in and you'll see that uh, when I click on this component, when I select this component, it'll sort of light this small cross where the centroid of my box is. Now, of course, this centroid is right now at the origin because my box base was at the origin. But essentially, wherever my box is, the centroid of that box will be the output of this. So that is what is being highlighted when I select this component. Right now, I needed the volume of this. So what I'm going to do is I'll come back to Grasshopper and I'll add a panel. You could either type in panel, or a quick shortcut is a double backslash. Right. There are a couple more shortcuts also, like the if you have a these symbols sort of there are a couple of symbols that let you that you can use as shortcuts for a lot of components. Anyway, so yeah, I've added a panel here. Now, a panel is a special kind of component which can act as a parameter whose data is visible. So if I plug my box in here, this panel now contains a box, and it's even showing me that it has a box. And if I plug this into my geometry, it will not work that way. But if I, so it works with text, which is string in programming terms, and numbers. So if you have a number or text, then you can basically plug in a panel to see what that number or text is. If you plug in any other kind of data into this, then it will give you a text representation of that data. Now, I've been saying data a lot, so I'll explain where data comes into the picture. So all of these lines that you see are essentially carrying data. Here, our number slider has a value, is emitting a value of 13.254 as its output. That output data is essentially going through this wire and into the x parameter of this component, so that all of these wires basically transport data. So I will come to the different kind of wires when we work with structures later on. Right, so here I have a very simple script which creates a box of any size and calculates the volume of it for you. Right, and also shows you the box, what it looks like. Fairly simple. Right, now think of the amount of work that you would have to do the same thing in, say, SketchUp or AutoCAD. Right, you would have to create that box manually and then run a different command that actually calculates the volume, and you'd have to do that every time to get to the right volume that you're expecting, or the right kind of box that you want. So that is sort of the sheer power of Grasshopper, that it sort of quickens any task for you. It'll make the uh, it'll make most tasks very, very quick, and avoid and let you avoid sort of repetitive uh, clicking and typing unnecessarily. So right, so a very simple script. Next, let's see how data works. So right now we're only working with single datum, essentially, right? The singular word for data is datum. So we're working with datum here, which is why our lines, our wires look like this, single lines, right? Only one number value is going into X, only one number value is going into Y, and 1 into z, then we are getting only one box, which is said here as well, one locally defined value. And then that box is going into this, which gives us one value for the volume and 1 point for the centroid, right? Now what happens if I make another copy of this number slider and set the value to something else? And actually I shouldn't do that, that will probably confuse you, but instead let's understand what base does, right? So base is essentially, it takes a base plane, which is this sort of grid that you see here, and you can enter uh, any plane into that. Now a plane, if I take an XY plane, right, this XY plane creates a plane that is parallel to the XY plane at any origin. So by default that origin is 0, 0, 0, but I can always set a point somewhere, right? I'll set a point maybe here, and we can take that point and it'll create this plane at that point, right? So now that I have this plane, if I plug this into my base, my box suddenly shifts from there to here, right? And if I select this point in Grasshopper, I can even move this around with my gumball on, right? So as I move the point, here point is a parameter. So as I move this point around in the Rhino viewport, my box is also moving around with it. The reason for that is that this point is a parameter of this plane component, and that plane that is coming as the output is a component, is a parameter for this box. Right now, what if I want two of these boxes of the same size in this space at 2 points? So I'll just make a copy of this point here, right? So I have now two of these, and going back to Rhino, I'll just move one of these points somewhere else. Right now, since this point isn't connected to any of these components, it doesn't affect any of my geometry. But if I simply plug this in while pressing shift and plug this into the origin, that basically takes whatever it already had as input, and also takes the new input wire that I've given it if I press shift, right? So control and trace, if you press control and trace a wire, it'll remove the wire from the viewport, from the canvas, and if you press shift and draw a wire, it'll not remove the existing wires and draw the one that you just drew as well, right? If you don't press anything, it will replace all the wires that were there before and create the one that you are drawing just now, right? So now I have 2 points as the origin for this XY plane, and so now you'll see that the wire coming out of plane is now a thick, double lined wire. Right? The reason for that is that now it contains a list of elements, a list of items. Basically, it has data now instead of datum. Right? So it has 2 planes that are coming out of it as output, and those 2 planes are now coming as coming into this center box as input, and so this center box now has 2 planes to draw boxes on. So it's going to draw 2 boxes, right? And it's going to then give those 2 boxes to the volume component, which is going to give you 2 values for the volume. Now, our boxes are essentially the same here, because the only difference between these two boxes right now is the origin of its plane. So if I change these sliders, both of these boxes sizes in the x direction will change simultaneously, and so will essentially the volumes. Right now, if I want this to be different, then I can simply create a copy of this number slider and press shift and plug that into my X. So now I have two numbers going into my X value and two planes. So what this component is going to do now is it's going to take the first value along with the first plane to create the first box. So if you look at the volume as well, if I move the first slider, only my first volume will change. If I change the second slider, the second volume will change. So that is essentially how data then starts to work in Grasshopper. And now you'll notice that performing this task manually again would be uh, incredibly time consuming, right? So it's saving you a lot of time uh, in avoiding repetitive tasks. Right now, uh, we are still working with only lists of items. Now in Grasshopper and just in computers in general, just okay. So the way data works in Grasshopper is draw it out for you. So let's stop thinking about Grasshopper and data for a second, and let's go into kind of a garden, right? Now, let's imagine a tree. What does a tree look like? It has a trunk, it has branches, and it has leaves, right? So essentially, it has a structure, and it has foliage. It has items on it, right? On that structure. There could be branches on branches and further, you know, that way. Now, let's think of each of these leaves as items, right? And let's understand that for us to be able to explain to a computer that this item has to be referenced with this particular item only, to sort of tell it that don't you know don't mix the wrong item with the wrong one, right? Always match the correct items. We use something called a structure in our data, right? Which very much resembles the structure of a tree, with with a trunk and branches, and further sub branches on those branches, and at the end there are leaves, and those leaves are our individual data items. So what we did here in our for our box is essentially uh, a very small plant, can't even call it a tree, with just two branches. Actually, sorry, is a very small plant with just one branch and two leaves, right? This point and this point, which becomes two planes, right? So this is essentially called a list. And so if I add a panel here, you'll see that there are just two values at index 0 and 1. Now, this index is basically what defines the kind of the roll number or the serial number of each of these items, right? It's the address of these items in the list. So the 0th item is this plane. The first item is this plane, right? So it's just a list of two items. So we have two leaves on our small plant. Same here, right? Those two leaves were processed by this component, and we still have just two leaves, right? And the same here. Now, actually, I should probably take a different example. Now let's. So this explains lists, right? Now let's take a different example and start with two curves, right? So I'll just open Rhino here and I'll define two very simple curves, and I'll add two curve parameters here, right? Now what I'm going to do is we'll come back to data after I've explained this example actually, right? So I'm going to reference these curves in my Grasshopper file. So I can simply right click on the curve and set one curve. Now it'll let me select a curve. So you can see curve or edge to reference is what it says in the command line. So I can select a curve and press enter or space, and now this parameter contains that curve. You can see it lit up green when I selected this parameter, right? Similarly, I'll reference another curve here. Now, what referencing does is if this curve happens to change in Rhino, that same curve is referenced in Grasshopper, so the value of that curve will also change. So now I have basically my parameter here is a real curve, right? And not an imaginary value or anything like that, right? So I'll simply divide these two curves into 10 segments, right? And for ease of understanding, I'll just use this. Don't worry about this wire just now. We'll come to that. Right, so I've divided these curves into 10 segments, which means that there are now 11 points on each of them, the first point being 0 and the last one being 10, right? And what I'm going to do is I want to essentially I want to join these two curves and each of their points with lines, right? This is what I want to see. So I'm going to add a line component like we had earlier, and now you'll notice that okay, ignore this, right? Ignore that I did that. That is just for understanding how these look, only pay attention to these. So I've done this twice, right? So I have divided these two curves and I have these 11 points for each of them. So say I want the starting point to be this and the end point to be this, right? And that's it. That does my job pretty well. Now why? Because this is a list of 11 points. This is another list of 11 points. So what it's going to do, it is going to match the first point of both these lists, then the second point of both these lists, the third point, and so on and so forth. And it's going to create 11 lines which start at each of these corresponding points and ends at each of these corresponding points. Right? Pretty simple. But now what if I want it to be slightly different? What if I want these two curves and I want the first line, the first point to connect to each of these points, then the second point to connect to each of these points, and so on. Right? That's it. Now, I'll explain what happened here. We had our trees, right? So if we have a list of 5 items, then Grasshopper will simply compare them in order. Right? 2 lists of 5 items each. If we have more items after this, or you know, the number of items in both the lists are not equal, it will, as soon as it reaches the end of one of these lists, it will wrap around, and so then it'll compare these two, then these two, and these two, and so on, right? If there's another, then these two. So that is how lists of items works. Now, say we have 3 items, then another 3 items, and another 3 items, or 4 actually. And these items are points, right, with various coordinates. Let's say each of these sets of points define the 4 points that are needed to make a quadrilateral, right? Now, of course, the simple way to do this would be to just add the component that does that and plug these 4 in, and it will give us our quadrilateral, right? Now, in Grasshopper, there's something that you should keep in mind, and that is that repetition should always be avoided, because that is why Grasshopper is there, right? You should, if you're repeating something, if you're repeating steps, if you're doing something that is repetitive while using Grasshopper, then you're doing something wrong, and you can do it in a better way for sure, right? Let's say we only want to use this component once that creates the rectangle for us. We can simply create a tree, a structure that has 3 branches, and each of those 3 branches has 4 items on them, right? Here we had just a single branch and 4 items on these single branches. And that is what this component was able to do with that single branch. So what if we plug this in, right? Here it took a branch with 4 items and gave us a branch with a single item. So what will happen here is the structure will remain exactly the same, right? Unless a component explicitly says that it is going to modify the structure remains the same. And it will give you the same output, right? With using these 4 points to create a square each. Right, so let's try this out in Grasshopper. Let's forget all this. Took the wrong example. Let's add 4-point parameters. Sorry, 3-point parameters. And let's set multiple points in each of them. 1, 2, 3, 4. Multiple points, 1, 2, 3, 4, and 1, 2, 3, 4. And let's use the polyline component to make each of these, right? And we'll make this closed. So as you can see, doing this thrice gave us these 3 quadrilaterals. Now if I had to make more, I would just have to keep on repeating this same task, right? Just copying this and moving the points around. But if I want to do this in one go, I can simply merge these 3, delete 2 of these. Right, and graft them. Now what grafting means is, I'll come to that first. I'll show you what this looks like. Right, now, okay, I'll first explain grafting. So let's say we have a list that has 4 items. If we graft this, we will get, instead of items, we will get 4 branches with 1 item each. So it takes a leaf and basically extends the stem and makes it a branch. That is what grafting does. Right? So if we have an existing structure with 2 items on each branch, grafting this will give us a structure that has 3 branches, then 2 sub branches, and 1 item on each of those branches, right? So this is essentially what grafting does. Now the opposite of this is flattening, right? Now if I flatten this structure, it will remove any existing structure that there is, and it will just give me all of the items in an ordered list. Right? It will remove any structure that there is. So when I do that to this structure, it will give me 1, 2, 3, 4, 5, 6. This is what I get. It'll remove any and all structure and give me a flattened list. Right, so this is graft and flatten. These are 2 data functions that are going to be really important. Right, so I've basically grafted these lists. So instead of being a list of 4 items each, These are now a list of 4 branches with one item on each branch. All 3 of these. Right. Now if I merge these and if I merge these 3 tree structures and I plug them into my polyline component, what I see is this, but this is not what I expected, right? The reason for that is if we look at this data here, you can see that there are now 4 branches like there are in each of these. And in fact, I'll just graft them. So you can graft any parameter anywhere. You can graft them. So I'll just graph these right here, right? So these were 4 branches with one item each. And so now when I've sort of merged them, it'll take merging 2 structures of the same, 2 data structures with the same structure will essentially give us the same structure, but with all the items in the order in which they were initially. So if this is 1, 2, 3, 4, 5, 6, 7, 8, 9, then this will be 1, 4, 5, 2, 6, 7, 3, 8, 9. Right, that is merging. The order also is retained here as well. So if this is 1, 2, 3, 4, these will be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and the same here. Right. So when we've merged these, we've got now the same 4 branches, but with 3 items each. So what happens when we plug this component in? It will start by creating the first polyline for the first branch, right? It'll go to the first item, then the second item, and the third item. And then it will close it, which is why we have a triangle. We have 4 triangles that we can see here. And these 4 triangles are the first item of each of these makes the first triangle. The second item of each of these makes the second triangle, and the third and the fourth. Right. Now let's think of this as a table. Oops. Right, so this is my number and this is my point. Right, so if I have my first branch essentially is, say, let's call this 1. Right, actually it should be 0, so let's call it 0. And we have 1, 2, 3 points here. Then 1 has 1, 2, 3 points here. And right. So this essentially means that if we want to instead have the opposite in the sense that we want our actually I'll draw this in a slightly different way. Sorry, ignore that. Right. So 0, 1, 2, 3. So here we have at our 0th branch, we have 3 points. At our first branch, we have 3 points, second and third. Instead, we want this to be this way, right? Our 0th branch should have 4 points. Our first branch should have 4 points, and our second should have 4 points, and in this exact order. So this, if you all remember matrices in maths, is what we call transposing a matrix, right? So here in Grasshopper, that's called flip matrix. So we'll simply, as you can see, now we have 3 branches, and essentially our columns and rows have been switched. So where we had 3 items in our first branch, we now have 4 items in our first branch. Now these items are the first branch, the first item of the first branch, the first item of the second branch, first item of the third, and first of the fourth. Then the second of the first, second of the second, and so on, right? Now if we plug this in, we'll have what we wanted, right? If any of you have any questions, but believe me, this is one of the most essential parts of being able to work with Grasshopper well. If you understand how data structures work, then working with Grasshopper is a breeze. So right now, if we did not want to do all this, if we simply wanted to get our 3 squares without having to do all this, we could simply, instead of having 3 point parameters, we would have to have 4 point parameters with 3 items each, and that would lead to this being flipped already, and we wouldn't have to do all this, right? But so that you were able to understand what flipping the data means. Now, keep in mind that if you have, okay, I think this is a good point to explain what these numbers are here, right? So let's go back to our garden with our trees, and I'll draw a really complex tree with the weirdest branches. Right. So let's say we have a structure like this, right? Now, each of these leaves essentially has what we can call an address, right? So, like us humans also have addresses. We say that I live at house number so and so, in street, this and that, and then city, then state, then country, and so on and so forth, right? Now, actually, let me write that out as well. And planet, and planet, and galaxy. So if we're all living in the same galaxy, we don't need to mention this. If we're all living on the same planet, we don't need to mention that or this. Maybe we're in the same city, right? So if you're talking about your address relative to someone who is at the same address, you don't need all this, right? Now this is very similar to our structure here, where this is our trunk and this is branch index, say 0, right? This is branch index 1, this is branch index 2, 3, 4, and 5. So if there are, say, here we have this leaf and this leaf, both these leaves are at branch 0, and then they are at branch 0 and 1. So if there are two items here, for example, then the address of this particular leaf would be 0, then 0, then 0, right? The address of this one would be 0, 0, 1. The address of these two leaves would be 0, 1, 0, 0, 1, 1. Now, if we come to this branch, I am doing it the other way around, but yeah, just let's just say that there is a branch at index 4, right? And then these are 1, 2, 3, sorry, 0, 1, 2. Always remember indices start from 0, right? So this particular leaf would be 4, 0, 0, right? So that is how we address each item in a data structure. So here, these are at branch 0, 0, 0, 1, 0, 2. The first 0 here is there because of uh, giving the trunk an index. So this trunk here also can be given an index of 0, right? If we have another trunk by any chance. Now, just like we didn't need our galaxy, planets, country, state here, since all of them are basically on the same trunk, we don't need these first in the first the first part of the address here. So we can simply right click on that parameter and click on simplify. What that does is it removes all redundant path elements. So the part of the path, the address that is redundant, that isn't required, is automatically removed. And so now we only have the indices of the branches, right? So that's essentially almost all that you'll need to understand when it comes to data. So we just need to know how to deal with items, lists, and trees. The wire looks like this when you're dealing with trees: thick and dotted, right? So the three kind of wires that there are, this is for a single item, this is for a list, and this is for a tree. Now, if you don't see these kind of wires, you should keep this on, draw fancy wires in display. Right. So now we know what data looks like, how it's used, and why it's important. We can actually start, using it in various ways. So what we're doing here essentially is we're creating algorithms that algorithms in the sense that these are definitions of three-dimensional geometry, right? So it's all in the background. All of this is mathematics. So, which is why this is often there is even a book called Algorithm Aided Design. So this essentially is algorithm aided design, where we are actually defining an algorithm, and based on that algorithm, we're we have parameters that go as input to that algorithm, and we get output from that algorithm. So let's try and make a really simple script of a really common thing that's called point attractors. Now, first, let's understand what a point attractor script would do and what it means, right? So imagine a single point, right? And you have various panels. Anyway, right? And you want to maybe open and close these panels based on their distance from the point. Right, these panels could be, let's shape them like this. Now, if this point is close to a panel, we want it to be extremely narrow. If it's far away from, right. Now, again, as I said this, I said that depending on the distance from the panels, which means that if I'm able to calculate the distance of this point from each of these panels, the amount by which these panels is opened is directly proportional to that distance. So let's go step by step. Let's first define our panels, and let's figure out a way to be able to open or close those panels. So I'll just make a I'll make not a rectangle. I will yeah, actually a rectangle, right? And I'll set its size as 1 by 1. Right, so we have our rectangle, and I'm sorry, I'm breezing past all of these components. Now, there are a lot of components and a lot of plugins that are available on online as well. So there is a website called I have it open here, Food for Rhino, where you can find all sorts of plugins for Grasshopper, and if you just search for a plugin, you'll be able to find it. So uh, pufferfish is probably the most commonly used plugin that there is. So this sort of uh, makes Grasshopper more powerful. It has a lot of components that weren't there originally in Grasshopper, but probably should have been. Right, so it has some 200, 400, and how many components? 300 components. And there are, other plugins. I have also worked on a couple of plugins that I've submitted. We also have a Grasshopper forum that where you can, post your queries, questions, and you can find other people's queries and questions as well. Right, so I am not going to be able to go through each and every one of these thousands of components. So it is really entirely up to you to sort of by yourself explore, what various components do and how they work. It's not at all difficult because all of them have descriptions. They're, just like any AutoCAD command or SketchUp tool. Uh, you just need to understand what inputs they take and what outputs they give. Uh, and on that basis, you should be able to work with just about any component that there is, right? So coming back to the script, we have our rectangle. So let's explode this because I want the points, the vertices of this rectangle, and the explode component will basically give me the segments and the vertices of any polyline curve. Right, so I have my 5 points because this is a closed curve. So now I want to remove that one redundant point. So I'll use a component that uh, culls the duplicate points. So now we'll have 4 points. Right. Now with these 4 points, I want to move them closer to the center of this. So first I will need my area, so that I can get my centroid. So I'll get this centroid as well. Now I want to move these. I want to move this point and this point closer to the center based on a number slider. So I'll create a number slider that ranges from 0 to 1 with a default value of 0.5. And based on the value of this number slider, it should either be completely closed at 0 or completely open at 1. So I will so I want to get only 2 of these points, right? So I'll create a component that this list item component. So it will give me one item from a list of items, right? So I want the first item, which is this one, and the uh, third item, which is this one. So index 0 as well as index 2. Right, so it gives me 2 items which correspond to these 2 points. And now I want to essentially scale them with respect to the centroid, which is the center. And I want to scale them by this factor. Right. So if this is 0, it will be extremely close to the center, and if it is 1, it will be extremely far from the center and closer to where they were originally when the value is 1. Right, so fairly simple. Right, now I can recreate my polyline, but first I need to get uh, my list of 4 items. So right now I have only 2. So instead of using the list item component, I can also use dispatch. This component does a very similar thing, just that it splits my list into 2, right? Wherein I will have 2 points coming out of one of these outputs and 2 coming out of the other. So once I have modified the ones that I need to, I can then merge these back together to get the original structure. And then, okay, and then close this. Sorry, I should probably weave these instead of so this component takes a dispatch pattern, which right now is set to true and false. So it'll start from the first item, and the first value is true. So it will give me the first item in list A. Then the second item is false, and so it'll give me the second value at B. Then it'll loop around and it'll give me the third item again true at list A, then the fourth item at list B. So it sort of splits my uh, list of values into uh, you know 2 lists that are based on a particular pattern. Now I could change this pattern, of course, and I could set it to true, true, false, or false, false, true, something like that. And the number of items in each of these lists and how they are coming from the original list would change accordingly. But we'll stick to this, and weave essentially does the same thing, just that it does the opposite. It takes the 0th stream first. It takes the first item from the stream from stream 0, then the first item from stream 1, then the second item from stream 0, the second item from stream 1, and creates one list. Right, so I basically dispatched and then weaved after modifying half of them. So I have what I needed, right? And I've closed the polyline, and this is essentially the inner panel. Right now I can create a surface using the boundary surfaces component. And with that, I have one of my panels working, right? Now what I'll do is I'll add 2 relays. Now a relay is basically a component that has just one input and one output and does nothing, right? It just takes data and gives it as it is. Now the reason why relays are useful is because if you have created a script like I've done here, and you only want to change things on this side of a relay, then you can add these and sort of group the rest of this, and you don't have to worry about what is going inside, what is going on beyond these relays. And it lets you sort of change the input to a script without modifying it too much, right? And I mean, these are really useful things. They'll come in handy in doing a lot of wire management later on when your scripts become extremely complicated and large. So now that we have one of these working, the first task is to create multiple rectangles. So, which means that we essentially need a list of rectangles. Now, there's a really good plugin called Lunchbox, which has a really nice component called quad panels, which lets me essentially uh, I can create any kind of surface, and which I will do here. Right, so I have a surface here. Let's set this to shaded and go to perspective. And I'll just reference this surface like I referenced my curve earlier, right here. And this sort of takes a surface and divides it into u and in two directions, in u and v dimensions. So I want to, let's say, divide both of these 11 times. I will get 121 panels. Now these panels are once again surfaces, so we just want the outer boundary of these surfaces, so we can uh, we can actually just plug these into a curve component, and it will give us only the polyline boundaries. And if we plug that into our existing script, it does something, but it's sort of messy. It doesn't look the way we want it to, right? The reason for that is now we have a list of rectangles, which uh, which it is converting into a tree of vertices, and then is modifying each of those vertices and then scaling them based on a list of centroids. So I mean, things have been bad right here. This is where things went bad. So what if we graphed our curves, right? Now all of a sudden it looks exactly the way we want it to. Right? We have multiple surfaces, each of which is controlled by this one slider. Just by grafting this, all of our structures are now the same. So all of them, okay, this is not the same, but if we simplify these, it'll be the same. It automatically does that in the background, but for your uh, for your better understanding, it's good to actually simplify it yourself as well. Right, and if at any point you have any doubt about how the tree structure looks, you can either add a panel, or there is a really neat component called the parameter viewer, which lets you see a tree structure like this, right? So it'll let you actually see and compare two different structures. So if, for example, this issue is coming here, right? If I don't craft this, you'll see that this is the tree structure from my geometry, and this is the tree structure for my centroid, which means that something is wrong with my centroid tree structure. If I graph this, both of them are the same, and so the output is predictable, right? So now I have solved one part of it, which is to get multiple panels. Now I want to basically change the size, change the amount uh, by which each of these panels is opened based on their distance from a point. So I'll just add a point parameter here and set one point somewhere, right? So if I move this point around, all the panels that are close to this point should be more open, and the ones that are far away should be more closed. So to do that, we already have, let's just delete this group. We already have the centroids of each of these, rectangles, each of these panels. So what we can do is we can calculate the distance between that centroid and this point. We now have a tree of distances that correspond to each of these centroids distance from the from this point, right? And we need to remap this to actually get values between 0 and 1. So the way we can do that is, now if we look at these values right now, these values range from, they're all really large or really small. They can go from like 10, 15 to 100, 150. We want these instead to be from 0 to 1 so that they can actually change the amount by which these panels are open. Right? To do that, we can remap these numbers. So what that means is, imagine a number line, right, from say 0 to 10, right, and we have all these values in between, and we have, say, we've selected 7 and 5 and 1, right? If we now suddenly want to, in a sense, scale these values from 0 to 100, it's pretty simple, right? The values will become 70, 50, and 10. But if we now want to change the position of these values, essentially from 0 to 100 instead to 100 to 200, then we will have to change these, we'll have to basically offset these values by 100, right? Now to get from here to here, we had to do two operations, right? Multiplication and addition. Remap essentially does both of these in a very quick and smart way, where it only requires the initial bounds of the points, of the numbers, and for that we have this component that takes a list of numbers and gives us a domain that defines the bounds of those numbers, and a target domain, which is in this case from 0 to 1. And if we check these values now, they're all, instead of being from 8 to 163, they're all now from 0 to 1, and are proportionally large or small as they were initially. So the largest value is now 1 and the smallest value is 0. So let's see what happens if we, instead of plugging this number slider into our scale, if we plug in our mapped values here. If you look at our Grasshopper viewport, this is our point, and as expected, all of the panels close to that point are open, and the ones that are far away from it are closed. So mission accomplished. Right. Now, a question that might have popped in your head is why is this one red and this one orange? The reason why this is red is because it has an error. It's giving an error saying that I cannot scale with the factor 0. So the lowest value in this list, when remapped from 0 to 1, one of those values, the lowest value, would have become 0, which I am unable to, yeah, this one. Right, now if you scale something by 0, it becomes essentially non-existent, right? I mean, it doesn't exist anymore. So this component can't really scale to 0. And similarly, if there is geometry that doesn't exist, that is null. So if we look at this, that one value at branch 80 will just say null, right? So if we take a null value and try and create boundary surfaces from it, then it just won't be able to. So this component is not giving an error, but it's giving a warning saying that planar surface routine return no results on that particular value, right? So if instead of 0 to 1, we say 0.1 to 1, those errors and values disappear. Right. And so essentially this is a very simple point attractor script. We can now increase the number of panels. We can change the kind of surface that we had. And as we do that, since these are all parameters, the entire script automatically updates. And so let me just rebuild this with right. And if you click anywhere with the middle mouse button, you'll see this wheel, which essentially has some really useful shortcuts. So these two heads, this disables the preview of the selected components, and this enables that. These two will disable or enable the actual component from working altogether, and we'll come to baking later. This button will zoom into all of the geometry that is being created by the selected components. This one will create a group of all of the selected components in the Grasshopper canvas, and we'll come to the rest later on. Actually, so this one will lock or disable the solver. So if I make changes to my script right now, it won't actually update. I'll have to recompute manually to make those changes to my script, which I can demonstrate like this. So if I change my point, it's just that these wires don't have any more data, so which is why the script is not running. If I unlock the solver, it'll run. Or if I change the script and hit recompute, it will run. Right. And yeah, group does this, and cluster essentially will take the selected components and make a smaller component out of them instead of so you can basically shorten your scripts using this. right? So yeah, we now have a script that takes just about any surface and creates panels on that, which depend on their distance from a given point. The closer they are to that point, the more open they'll be. Simple enough, right? Cool. So we've understood uh, the basics of Grasshopper, how components work, how data works inside of Grasshopper, and we've understood how geometry and data of geometry can be used to create algorithms that do exactly what you intend to do with them. And so I'll just go through a couple of these the various data types that there are in Grasshopper, so that it can sort of give you an idea of what all is possible. So we have, of course, points, vectors. The primitives are Boolean, integer, text, and number. Right? These four are like the most basic uh, parameters that there are. So Boolean essentially contains either a true or a false value. Integer will contain a value which is an integer. It will not have a decimal place. Number will have as many decimal places as you need. Text will contain a string of text. Then you have color, complex numbers, domains, and matrices, time, file paths. Then we come to geometric parameters like points, vectors, circles. So all of these parameters essentially let you contain this kind of data, right? And all of these components will let you modify that data and get an output based on what kind of component you're using. So let's say you want to maybe move a line, right? So moving, rotating, and scaling all come under transform, right? So moving essentially is called translation. So scale, move, and rotate. These are the three essential translations that there are, right? And the way these particular ones work is that if you move geometry, it will keep showing that geometry to you as well, because uh, that has not been hidden, but the output will be the moved geometry. And you will also get transforms out of this, right? And you can actually modify transforms. You can compound them to sort of get one transform value that, when applied to any geometry, will perform all of these transforms at once. Right. I won't get into the details of how transforms are constructed with matrices and all, because that involves a lot of maths. Uh, but at the end of the day, geometry is essentially a subset of mathematics. So you will find yourself, you know, trying to grasp mathematical concepts a lot if you try creating complicated scripts, right? Especially for architects, if you start to do things like this, if you want to create facade systems or something that is geometrically complex, then understanding the mathematics behind geometry becomes really important. So which is why having an understanding of that mathematics is crucial. And for that, there is a book called Essential Mathematics by this one. So this book will contain all. I'll add this to the YouTube chat. So this book contains sort of all of the basic mathematical concepts that are required to understand how geometry works, especially in Grasshopper with vectors and points and planes. Okay, one thing that I sort of forgot to explain is breps and meshes. So for those of you who have worked with SketchUp, you will be very familiar with mesh geometry. Right? Now, meshes essentially are let me actually create two spheres. Let's hide all of this. So these are two components that basically make spheres, but one is called just sphere and the other is called mesh sphere. Right? Both of them do essentially the same thing, except that this sphere will give me a surface, an untrimmed surface. Now, Rhino works with a library called NURBS, NURBS. And what NURBS essentially means is that NURBS geometry is defined by a mathematical definition in the code. So this sphere is in the background defined by some mathematical definition that the computer is able to understand. And so it is extremely, extremely accurate. If you were to find any point on this surface, if you were to evaluate any point on this surface, you would get the most accurate values possible, right? And the reason for that is that this is mathematically defined, right? So you can see that the coordinates of each of these points is extremely accurate, right? Whereas if I evaluate this mesh in the same way, right. I mean, so a mesh essentially, the difference between a mesh and a brep is that a mesh is not that accurate. It will be made up of triangles and if you press Control M while Grasshopper is selected, you will be able to see the lines of the boundaries of the mesh faces. So you can see here that each mesh is made up of triangles and quadrilaterals. Right. If I triangulate this mesh further, you can see that it's entirely made up of just triangles, right? And so these triangles by themselves are flat. So if I want to get the value of a point that is within one of these triangles, the coordinates of a point that is somewhere here, or not exactly at one of these vertices of these triangles, then the value will not be really accurate, not as accurate as this will be. So that essentially ends up being the main difference between a BREP and a mesh. A BREP is stands for boundary representation, which is a sort of culmination of multiple surfaces, uh, wherein each of those surfaces act as a boundary and sort of have a enclosed space, enclosed volume. Um, Something called a solid in SketchUp would be the best comparison. In 3D printing terms, it's called watertight. Being watertight, a watertight uh, object is something that has no holes. So if you were to fill it, then there would be no holes for it to come out of. So boundary representation is a closed BREP would be a boundary representation which has no holes. And similarly, a closed mesh would be a mesh with uh, no holes, right? And since their entire definition is a mesh is defined by polygons and triangles and quadrilaterals, and a surface is defined by a mathematical function. Since their definition itself is so different, the uses of these two types of geometry is also drastically different. So while working with mathematical definitions of geometry, I would highly recommend working only with NURBS geometry and not using meshes at any point, uh, unless the mathematical the functions that you have to perform are easier on a mesh, and only while you are sort of only when you are uh, rendering or exporting or uh, doing something that uh, does not require high amount of accuracy is when you should convert it into a mesh, right? So for example, if I want to export this now to SketchUp being a mesh modeling tool altogether, I would have to either I would have to directly export it and it would automatically become a mesh, or I could define how accurate I want my mesh to be. So I could take the BREP and like I've done here, I could set the settings as either high quality or as high speed, and the high speed settings would give me a less accurate mesh, which would have you know less triangles, less polygons. And if I were to do it with high quality, it would end up having more polygons or more vertices, either of the two, right? So that is meshes and BREPs. Uh, Now, with that being said, another really important concept is baking. So let's come back to our script of with the panels. And now, for example, I've got this right now. I want to export this into Revit or SketchUp or AutoCAD or something. So for that, I can't really just copy data from here and paste it there. So if I right click on any parameter that contains geometry, I'll see this this one option that says bake. Now, remember, this script is like telling Grasshopper how to bake a cake, right? Each of these are steps in the recipe, and all of this data is like each of the ingredients required, right? So these four parameters: the surface on which the panels are to be made, the U and V divisions, and the point. These are my four ingredients, and this is my entire definition of the recipe, how to take these four ingredients and make my cake, right? At the end, all I have to do is bake the cake. So now that cake, which till now has been in Rhino's imagination, in Grasshopper's definition, and colored red and green, can now be baked. And if I turn off the Rhino preview by clicking on this button, I can see that that same geometry is now actual geometry in Rhino and can be selected. Right, imaginary geometry that was part of Grasshopper cannot be selected in the Grasshopper viewport, in the Rhino viewport. Now it is actual geometry that I can within within Rhino as well modify, right? And now I can even go ahead and export this or save this file as a 3DM model or even a SketchUp model, or however, even a object or FBX. Rhino is really good at exporting and importing things as long as you don't use export and import commands and you save and open. Right, so now this geometry can actually be used somewhere, and say for example I want to create multiple options for my client or my boss or whoever, right? And I want to change certain parameters. I can simply move this model aside and bake another iteration essentially of the same definition. So the difference I made is very slight, but you can see. So now I have two iterations of the same thing. Now if my client doesn't like this one, they can go with this one. Or if they say, no, I want the panels to be open in this area and not in that area, then I can simply move this point around and then bake it again. And like that, I'm able to rapidly prototype my designs without having to, do the same repetitive task over and over again. Now, once again, I'll say the same thing. Like if we were making those boxes and calculating the volume, if we were doing this particular task in, say, SketchUp or AutoCAD, it would have taken ages to make even one of these, and then to change a parameter and actually change the surface or change the scale of one of these. If you've used any of those softwares before, you can obviously understand how difficult it would be, and Grasshopper makes it a matter of seconds, as long as it knows exactly what to do. And what you've actually told it to do is essentially the same as the commands that you would use when you would do the same in AutoCAD, or the tools that you would use when you would do the same in SketchUp, right? You just did all of that once, and just by changing the ingredients of the recipe slightly, your cake is drastically different. Right, so that is the main advantage of using parametric tools like Grasshopper. Now there are other software as well, like Dynamo and and there are a couple of them, right? Like you have Unreal Engine's Blueprint Editor as well. The main reason why Grasshopper is as popular as it is because of its community and because of the sheer number of people that develop for Grasshopper and support Grasshopper in all its forums and so Food for Rhino is a really great example of that. It currently has about 800 plus plugins, and I mean the number of users is just staggering compared to. So the community in that Rhino has is uh, really active and really supportive, which is why it is as popular as it is. Right. So I think one last topic that I should probably cover is plugins. You can see I have a whole bunch of them. Uh, Not all of these are very useful for me every day, but some of these are really essential, like Lunchbox, Pufferfish, Headruptor, and uh, a lot of uh, a lot of really old plugins as well. Right now, uh, to install a plugin in Grasshopper is something that uh, you will be doing a lot, especially if you're just starting out. So, for that reason, I'll just show you how to download and install Pufferfish as an example. So, you will have to create a login, sorry, an account on Food for Rhino, which is free, of course, and you can download any plugin. Now, most plugins will should download as a zip file, but if they don't, they're essentially a GHA file, right? So for pufferfish, we have pufferfish 2.2-8 dot GHA, right? Now, the first task that you need to do to install any plugin is to right click on it, go to its properties, and make sure that there is nothing here. If there is something here, it will basically say something along the lines of that this file has been blocked for security purposes or something like that. And there'll be a small checkbox that says unblock. Now make sure to click on that checkbox to unblock the file and click OK. Right, this is a security feature because that Windows has, because GHA files are essentially scripts, right? They're program files that can be run. So, which is why they're sort of blocked by default if you download them from an unknown source. Once you've done that, you want to go to File, Special Folders, and Components folder in Grasshopper, and you should see a folder that is called Libraries. It won't be this clean initially for you because I've basically moved all of my plugins here. It will have a couple of plugins with Kangaroo and all of these being installed by default. So you just need to basically paste your GHA file or all the additional files that are required as well right here. Right, so I had pufferfish 2.7 installed. I have now copied 2.8, and now what I'll have to do is I'll have to close this, close Rhino, and I'll have to delete the old file, and now I'll have to restart Rhino. and then run Grasshopper. And that will, now it will load my new pufferfish plugin. Right. Uh, Also, there are a lot of preferences that you can set for Grasshopper, like the palette, viewport. There are a couple of widgets that are really cool. So, for example, you have a really messy script and you want to make it a little more organized. There's this uh, Mr. Sparkle plugin that is installed by default that lets you sort of arrange and align your uh, components in a neat way, right? Otherwise, there is also uh, the uh, the profiler widget, which actually shows how long it took to run a particular component. So you can actually look at the component and understand how long which component is affecting your script the most. So I added a parameter plane mesh, and so this particular component is taking 19 milliseconds to run. So if I have a whole bunch of components and my entire script is taking about a second to run, I can actually go and see which of my components is taking the most time to run and optimize that. Right. And of course, always remember that while working with Grasshopper, don't do what I did just now and close everything without worrying about your Grasshopper file. You actually have to save your Grasshopper file as well as your model in case you have referenced geometry, right? Because the Grasshopper file is just this definition, which will be saved as a gh file .gh, and your Rhino model is completely separate. It will be saved as a normal 3DM file, and what you want to do is save both of these files together in the same folder so that it's easier to open them again later on, right? And yeah, that's about it for the basics. Uh, there are a lot of, like, it's a vast world, right? There are a lot of components that we have not discussed, like and not even touched upon, like Galapagos and Firefly and Kangaroo uh, and loops inside of Grasshopper. Right, I should probably touch upon that. So you cannot do this if you have some sort of script somewhere, that does something. Then you cannot close your wires in a closed loop. It will essentially give you errors saying cyclic data stream detected, and that is because Grasshopper only works from left to right in one direction. It does not let you make loops. For that, we have a plugin called Anemone, which is specifically designed to create loops. And yeah, that's about it. The rest, for the rest, I think the best is to keep practicing, keep doing various experiments on Grasshopper and trying different kind of things out. If you know any basic programming in Visual Basic, C Sharp, or Python, there are these really useful components that let you uh, just double click and write code inside in Visual Basic or in C Sharp or in Python, and run that script within Rhino. within Grasshopper, and create your own components essentially. Uh, I am tired of speaking now, so yeah, this this about wraps it up. And if you have any queries, any doubts, feel free to comment below, and I will try my best to clarify any of that. Right. Thank you. Hope you learned something from this. Um, and yeah, that's it. Thanks a lot for tuning in, those who are watching live, and those who are watching this later on. Feel free to share this and share it with your friends. If especially during this time, it's a difficult time all around during this pandemic, and it's important that all of us not only keep learning new things but also spread whatever knowledge we have, so that people, uh, you know, knowledge is sort of shared during a global crisis. And yeah, let's help each other out and stay safe. Right. Thanks. Bye bye.